Elements of Geology. This is going to be the introductory chapter today that I'll be lecturing on. As you can see here, we do have our set of PowerPoints, which you also have available to you on Blackboard. Starting off, we would like to take a look at the Earth's four kind of spheres, realms of the Earth, and how they interact with one another. Earth as a system is something we do want to stress. So we'll be taking a look at that. We will also look at Earth's resources and some of the problems that come along from trying to extract and use some of Earth's resources. So quite a bit to cover today. We'll also end with this chapter, the scientific method, looking through there and exactly what we mean by a scientific theory. So we'll end with that. But to start off, what is Earth science? As you can see here, we've got four main categories or sub-disciplines of the Earth sciences. Our first one here, geology. So you are in the geology course, so we will be really emphasizing the geology part, but Earth is a system that does have many parts to it. So we do look at oceanography, so the world's oceans, more or less a global ocean. Atmospheric science, better known as meteorology, we'll be taking a look at that. And astronomy. So astronomy takes a look at the Earth, yes, but also the other planets in the solar system. And it goes a little further and takes a look at the universe as a whole. So we will in turn get a look at each of these as we go through our PowerPoint. So starting off, we'll take a look at geology, that sub-discipline of the Earth sciences. And it gets cut into two main branches. The first one here is the physical geology. This pertains to the building blocks of rocks, so minerals and rocks. It will take a close look at the internal processes. So that is what this course will focus in on, those internal processes, the workings of the Earth, things that drive our volcanism and our earthquakes. And so plate tectonics is a theory we'll present to you, sort of an overarching theory that makes geology make sense. So we'll definitely be devoting time to that as well, but the internal processes. Geology also covers external processes, and so things like erosion and weathering of the Earth material, and then of course it's going to get transported and deposited somewhere down the line, and so the sculpting of the landscape, sort of the external processes. And of course we do have energy that drives each of these processes, internal versus external, a little bit different energy sources, and so we'll take a closer look at those. Historical geology is a branch of geology that looks at the physical changes over the expanse of the Earth's history. And the Earth is considered to be, by geologists, astronomers, and other scientists, cumulatively, 4.6 billion, with a B, billion years old. And so, with that 4.6 billion year history, there's a lot of physical changes that have occurred. And the geology, historical geology, does study that. As right alongside of the physical changes to the Earth, we do see the biological changes. After some time, life did evolve on our planet, and so we put together almost side by side, looking at the rock history that we can see through fossils. We get a look and a glimpse at what occurs with the biology, with the living organisms right alongside the physical changes. of the Earth. And so that historical side of geology deals with that. I brought with me a sample of rugose coral, just to give you an idea of how fossils can help us in the study of the Earth's history. Switch over here and see if we can see this under the camera here. We'll see if that works. But what we have here, a lot of focus in on that, is a sample of rugose coral. These are extinct coral. This sample is from northern Arkansas. So you're thinking, Arkansas doesn't have any ocean, so how do we have coral fossils in Arkansas? And that's a very good question. So what this rock here can tell us, it's in some limestone there, and this is a 300-million-year-old sample. And it contains these little solitary coral samples. So these little round specimens right there, little solitary rugose coral is what they call those. So these lived some 300 million years ago. They are now extinct. But from northern Arkansas, this specimen was found. So what that can tell us then, what do our corals need nowadays to survive? They need warm, shallow seas, fairly clear water so that they can get the photosynthesis to occur and get their nutrition. So warm, shallow seas. So this fossil by itself can tell us something about past environments here in Arkansas and of course around the world. But it let us know that yes, we did have at one time in Arkansas's history being covered by shallow sea-like environment, warmer kind of a climate as well. So fossils can tell us a lot about Earth's past history, the physical changes of Earth, as well as the biological changes as well. So historical geology, a very interesting branch of the geology sub-discipline. Okay, that's sort of the geology sub-discipline. Oceanography, so this is the study of the world or the global ocean. We do separate those into, Pacific and Atlantic and etc. But it really is a global ocean. And so oceanography hones in on the expanse of sort of the hydrosphere here. The Earth is covered by 70% of Earth's surface is covered by the ocean, so it's a very important category. But we look at seawater composition. So what is it made of? Lots of salts, as you would guess, but it's movement. So circulation. We do have surface circulation. We have deep ocean circulation that we look at. What is happening along the coast? So coastal processes. There's a lot of wave action and erosion that goes on, the breaking down and movement of earth material. So coastal processes. Seafloor topography, so topography, the lay of the land or the shape of the land. There's quite an interesting terrain beneath the ocean, and so we'll take a little bit of a look at that as well, the topography. And of course, marine life, because the ocean is filled, just teeming with living organisms. So marine life is part of the study of oceanography, a sub-discipline of the earth sciences. Atmospheric sciences. And so this branch is usually known as meteorology. So the study of the atmosphere is known as meteorology. And this is going to, of course, encompass the weather. So weather elements, wind, wind speed, wind direction, precipitation. Do we have cloud cover? What's the barometric pressure? What's the temperature? So all these weather kind of elements. So the study of the weather is known as meteorology. And weather is more or less what your conditions conditions are at this moment, a particular location and time. Climate, on the other hand, as we see up there, climate is the study of the average of these weather elements that I mentioned, and it's usually done over a 30-year period, an average. So that would be more of a climate, what a location would have, the average weather a location would have. That's more or less our climate. The composition of the atmosphere, so we do look at the atmosphere in the vertical and take a look at how it does change with temperature and pressure as you go up into the atmosphere. That does change. So we do look at its composition, what gases, is this thin, beautiful mixture of gases that envelops the earth. And we're very thankful that we do have an atmosphere because it does protect us from harmful radiation from the sun. And so it looks at also the energy coming in and coming out and through our atmosphere. So we take good looks at that as well. And so as this picture here, you can see there's a little tornado tearing through a flat-lying farmland kind of rural community there. And so the energy is tremendous that goes through our atmosphere. And so that is what the branch of atmospheric sciences or meteorology, the study of the atmosphere, is the primary focus of meteorology. So that's a subdiscipline of the atmospheric realm of our Earth, of the Earth sciences. And then we have astronomy, as I mentioned before, the study of, yes, planets, including the Earth, but we use the Earth to compare the other planets with. That's sort of a study of the planets known as planetology. It can tell us a lot about our own planet when we learn about other planets within our solar system. But it also looks at the origin of the solar system. How did we begin with our solar system? What is its composition? Sort of how it's divided up because of differences in the composition of the planets. And then they do branch out further with the universe, its origin and its composition. And so that would be something you would learn about in an astronomy course. So all of these four that I previously mentioned are sub-disciplines of the earth sciences. Okay, so I did mention the four spheres of the earth. I was hinting around at that. I did mention the hydrosphere. That is our water portion of the planet. And so they have this beautiful picture here of Earth from space. And you do, it's very strikingly, you do notice that it is blue. We are the blue planet, sometimes we are called. And it is because of the water covering our surface. And so it does cover about 71% of the surface is covered by water, and 97% of the volume of water is contained in our oceans, okay, in that global ocean we talked about. That's a tremendous amount of water on the planet, so most of it is tied up in the ocean. And so that leaves just a little bit of fresh water. It's about 3% of fresh water on the surface, yes, and most of that is tied up in our glaciers and is frozen, and so we can't use that either. And so that leaves us just about 1% here of fresh water usable to humans that is found in groundwater and in our rivers and our lakes as well. So out of all that water that we have, this planet covered with water, we can only use just a fraction of it, of the fresh water. So the hydrosphere. So I'm going to be drawing a little Venn diagram and have each of these spheres just to show that they do interact. We might talk about them separately, but all of these spheres, the four spheres of the Earth, are continuously interacting with one another, so you really can't separate them. from one another. They do interact with one another. But we'll kind of talk about them in turn here. So the hydrosphere is the water portion. The atmosphere, as we talked just a moment about, the meteorology course, the primary focus on the atmosphere. We study the weather elements, as I mentioned before, and we also study climate, which is the average of these weather elements, usually over a 30-year rolling kind of an average is pretty typical in there. And that's that thin mixture, envelope of gases encircling the Earth. And then the geosphere, so this is the rigid portion of the Earth. So it entails several layers in the Earth. So if we look at the internal portion of the Earth, we do see that we have an inner solid core, a liquid outer core, and then you go a little further out, you have what we call the mantle, motion in that, very high density rock. And then you have this thinner, you can really see how thin the outer crust is. So the crust, mantle, and core are sort of the different layers within the Earth. And if you can notice here, I don't know how well it'll show up, but again, you do have these PowerPoints available to you. We have two types of crust. So we do have the oceanic crust, which is a much thinner crust, and it is a more dense crust material, in contrast to the continental crust. And so the continental crust is a much less dense type of material. So we do have a contrast in the oceanic crust versus continental crust, which will become very important to us when we start talking about the plate tectonics theory, because those plates do move and they're going to interact with one another, and when they do interact with one another, what happens? So if one is less dense, one is more dense, you are going to get one sliding beneath the other. And so we get all kinds of interesting things that happen when the crustal plates do interact. So this is a very dynamic planet. It is continuously in motion. Okay, and so that's taking a look at the geosphere realm to our Earth system. And then, of course, we must not forget about the biosphere, because you and all living organisms are part of the biosphere. And honestly, it influences the other three spheres. They are all continuously interacting. But I tell you, if we didn't have life on the planet, our other spheres would be quite different. So it's very important. It includes all life, and it strongly influences the other three spheres. Without life, the makeup and the nature of the other spheres would be quite different. So the interaction of these spheres, then, I'm trying to draw here a little Venn diagram. So maybe we have the geosphere, so that's the letter G, the biosphere, the hydrosphere, and the atmosphere. So we've got all these spheres interacting with one another in a little Venn diagram. So we see that they're kind of all overlapping with one another. So what I like to think of, there's my picture, the four spheres of Earth interacting, I always think of a beach scene, which is what I have up here, the Santa Monica beach in California. And so what we can see here, we see the beachy sand, so this would be part of the geosphere. Of course, we see the ocean and the waves kind of coming towards the shore here, so the ocean would be part of the hydrosphere. We see sort of hazily the atmosphere, a little bit of haze, a little bit of clouds up there in the atmosphere. We also see a seagull in the air also, so that would be part of the biosphere. there, or let's say maybe you were standing here with your feet in the geosphere with water, the hydrosphere lapping up on you, part of the biosphere, and you're enjoying the wonderful salty kind of air, the atmosphere. And in the background here, you also see some mountain terrain there. So again, part of the geosphere. So a beach scene is a great way to remember that Earth does interact. All these four spheres do interact with one another. Interrelationships. So even though we might talk about them separately or focus in on one sphere over another sphere, you really cannot separate them. So Earth as a system, as I mentioned before, so the hydrologic cycle, so this is our water cycle. We have water vapor actually in the atmosphere that can create clouds. So those water vapor droplets will condense, creating clouds, and then you can get precipitation coming back down. So we do have that interacting atmosphere and geosphere and hydrosphere, all kind of interacting in our hydrologic cycle. The tectonics, so as I mentioned, plate tectonics, the motion of Earth's crust. What is actually causing that motion? So we'll learn more about that, but those plates do move and they do interact through volcanism, through earthquakes, so definitely interacting. And our climatic cycle as well. So kind of averaging all those weather elements and how that changes over time, the climatic cycle. So it involves processes, and those processes make products, and these are all driven by energy. So we do talk about an internal source of energy and an external source of energy. And so in the internal source of energy, which we will really focus in on, because it is what drives plate tectonics, it's what drives volcanism, and of course then earthquakes as well. So we will focus in on the internal source of energy in this course, but there is also an external source as well. But the internal source is known as radioactivity, so the spontaneous breaking down of atoms, okay? So breaking apart and then releasing energy. So internally, Earth's internal structure is very hot. So when the Earth formed, it was completely molten, and then it began to cool, and its internal part is still very hot and molten, and that heat is trying to make its way out to the surface, from where it's very hot to where it's cooler. So it's trying to make its way out, and as it does that, we are going to get motion of the crustal plates. And so that very much does drive the plate tectonics theory in there. But radioactivity, spontaneously breaking down, we call that decay, and releasing that energy, that pent-up energy in there. Really driving volcanism, earthquakes, and plate tectonics as well. The external source, this would be something that we would focus in on in the Earth and Atmosphere course, sort of external things. And that's the sun. So the sun does drive our hydrologic cycle, our water cycle. The sun will cause water to evaporate up into the atmosphere. And so you get your water cycle in this manner. So it does drive sort of our hydrologic cycle and our climatic cycle as well. So forming clouds and precipitating and such. So that is the external one. We may not really focus in on that so much in here, but it does become important in another course called Earth and Atmosphere. So, but we do have those two sources of energy. Okay, in the earth sciences, you do encounter scale that can go from seconds, so if we think of time, seconds to, as I mentioned, billions of years. The Earth is 4.6 billion years old very long history that it has. So it can go from seconds, saying these little chemical reactions take just seconds and that sort of thing, to billions of years to think about. And scale is another one in as far as sizes and distances. You will encounter sizes and distances if we start talking about the solar system, and then we talk about the galaxy, and you talk about the universe as well, all in the realm of astronomy subdiscipline. Yeah, you can go from just millimeters to billions of meters, and astronomers have made up even new units of measurement. Maybe you've heard of the light year or the parsec, because the distances become so large, they needed to come up with some new units of measurement. So you really will encounter a variety of scale when you study the earth sciences. Okay, let's see here. The environment. Okay, so on the earth, this is everything that basically surrounds you is your environment, and that could be your social environment. We all seem to have our cell phones at the tips of our fingertips here. So socially, our face-to-face conversations, your social environment, the biological environment. So, of course, all the organisms around you, all the living organisms, all the plants around you. Your physical environment, things like water, the air, of course, we breathe. This comes in the realm of the atmosphere, so weather and climate taking place. The earth, so the sort of soil and the rocks, and of course the minerals make up the rocks. These are what they consider an environment. And so the earth scientist does take a look at your environment and really helps to solve problems, environmental problems. We extract and use Earth's resources to have our, civilizations and our modern conveniences, our energy sources. And so the extraction of those resources and the utilization of those resources as well can present some environmental problems. And the earth scientist does take a look at those and try to give the most economical and environmentally friendly solutions to those problems. That's sort of the work of an earth scientist. Before we continue with the resources, we will real quick. I do want to pop this under the screen. This is Arkansas's state kind of a map here. Switch over real quick here. That rugose coral. Beautiful specimen. But I wanted to show you this. I'll refer to this very, very often. This is Arkansas's state map. Okay. Here's Monticello way down here. Put that all in view. Monticello way down there. So this map is a geographical province map where it separates Arkansas into its geology of the rocks and separates it into several provinces, we call them. And so you see how this is set up. We've got the Ozark Mountains to the north. We've got the Arkansas River Valley. We've got the Ouachita Mountain region. You've got the Gulf Coastal Plain, which Monticello is in the Gulf Coastal Plain. And then pretty much all along this side here, the eastern part of Arkansas, is the Mississippi River Alluvial Plain. And then we've got a little piece in here called Crowley's Ridge. And so this is separated into the geographical stratigraphic provinces. What is going on with the geology, the rock bed of Arkansas. And so I will refer to this quite frequently. You do have a copy of this on Blackboard, so you can get you a copy, and if you come to class, in class lecture, I would give you an actual handout of that. But it's listing several cities on there. Maybe you're familiar with Arkansas cities, maybe you're not. But we'll be kind of pointing out some of these cities, and so it's nice to see the location that I'm referring to, where it could be an earth resource, it might be just a name of a city, different things, and I'll continue to bring this out the entire semester as we end up talking about these and looking at the structural geology, of course the planet as a whole, but also taking a close look at Arkansas as well. So just for a moment there, we pop that under there, and I may have it back and forth under there as well. Okay, so when we talk about earth resources, we talk about two categories, renewable and non-renewable. So renewable resources are those that can be replenished in a relatively short span of time. So we think about within a human lifetime, let's say, or shorter, because we need to be able to use them regularly and not have to wait hundreds of millions of years in order to use them. So those things that can be renewed in a short span of time, say on the human time scale, are known as renewable. So certainly plants, the timber that we harvest here in southeast Arkansas, all the beautiful timber that we have, can be considered renewable, a renewable resource. Of course, animals, so in agriculture, our cows, cattle, and pigs, and livestock basically are considered renewable resources. Things that they consider renewable, things like wind. When you can get a location with consistent wind, like down here where we live, we don't get real consistent wind. But maybe up the northern part of the state, you get more to the elevated terrain in the mountain regions. Maybe you're going to get more consistent winds where you could tap into with those huge windmill kind of things to get some energy from that. And they would call that renewable energy resource. And water, so some places have tides that go in and out on a regular daily basis, that they could tap into the energy of water. We do put up dams to control water flow, and so you can get energy from that as well, but you can't put a dam up everywhere. So some places could have where they could use water as a renewable energy source. Solar, so the sun. Yeah, there are some places that don't have very sunny days that might not be able to do that, but solar power is an option for renewable resources that the earth has. And so renewable in a short, on a human time scale, kind of a means, those would be renewable resources. Non-renewable, on the other hand, are not replenished within a human time frame where it would be useful for us. So these take, thousands to millions of years or hundreds of millions of years. So we pretty much need to consider them as being finite, and that once we use them all, we're not going to be able to get any more of it in a timely manner. So that is non-renewable resources. So things like our metals, so iron, copper, aluminum, so we'll kind of take a look at each of those, our metals here. And then things we call hydrocarbon fuels as well. We'll be looking at each of these in turn. Things like the gas, the oil, and coal as well. So I'm pretty much going to be on this PowerPoint for a little while as we go through these. May put the camera document on from time to time as well. So some sort of mineral that gets mined that contains a metal in it. So modern civilizations we really do need the iron, building our bridges and our buildings and that sort of thing. So we do need iron for those. Copper, so our wiring, we have copper piping, these sort of things we need copper for. Aluminum. We actually do have an aluminum resource here in Arkansas that they used to do a lot of mining for, not so much anymore. But the aluminum, grab my sample here. I've got a little bit of aluminum foil here. So we have the rock known as bauxite. So I'm going to put bauxite right up here under the camera for you. Also going to write that name of bauxite. See if we can focus in on that any better. Not too bad there. So the bauxite. Maybe some of you from Arkansas are aware that this is the state rock, Arkansas State Rock. Known as bauxite. So it is an aluminum oxide, is its mineral composition to it. And so they used to mine it quite a lot. There's a city called Bauxite, Arkansas, kind of south of Little Rock, if you're familiar with that area, where they used to do a lot of mining. They still do a little bit of mining, I'm told. They actually have the Bauxite Miners as a high school mascot. So here we have a rock, an earth material that is the name of a city, name of a high school mascot as well. But it's stemming from the mining that was done for this ore. They needed to get that aluminum. Now our aluminum kind of comes from Jamaica, so it's kind of an expensive process. So you end up taking about 4 pounds, say, of the rock and making about a pound of the aluminum that you want. So it's a rather costly process here. But this is bauxite, and that is, you might want to make a note, Arkansas's state rock. Okay, so that's aluminum resource that we do have. We really don't have a lot of iron, maybe a little bit of iron, a little bit of the copper, really not much at all here in Arkansas with those, but yeah, the bauxite, and they don't use it too much now as they used to, but now it's more Jamaica and Australia, a little more cost effective to import that now. Okay, and of course that would be considered a non-renewable resource, okay, so taking millions of years in the making to replace that. We do have some lead resource. That wasn't one of the metals listed in the PowerPoint, but we do have a little bit of lead resource in a mineral here we have called galena, and it's a lead sulfide. Put the galena under here for you. Very shiny, kind of metallic look to the galena. Kind of a heavy mineral as well. So for those of you in the lab, you'll be studying a set of minerals, and galena is one of those. But this is a lead sulfide, so it does have some of that lead in it. And there's a city in Arkansas, in northern Arkansas, called Lead Hill. So that is the name of the city, and it's stemming from the resource, the earth resource of galena, or the lead that the galena contains. So there we have cities, towns named after earth resources. So geology, it's all around you. Okay, so those are some of the, oh, and we make these little sink shocks out of the galena. Maybe you're familiar with that, with fishing as well, these little beads, pellets there. So a few resources that we have here in Arkansas. Now, the PowerPoint didn't show non-metallic resources, but we do have some, most notably, we have like the purest of the, what we call novaculite. And so it's a quartz, microcrystalline quartz known as novaculite. Okay, so here I have a quartz crystal. These would be non-metallic though. We'll learn sort of some of the mineralogy as we go through our mineral unit. But this here is a little sample of quartz. I don't know the best angle to show that, or if it would show it better. Yeah, with a darker background there. So here is a quartz mineral. The hot springs area here in Arkansas. So the Ouachita Mountain region. Let me get my map real quick and place that in there really just for a second. Okay, so if you're not familiar with Arkansas, or if you grew up here and you're just not aware of some of these things. But here's Hot Springs, located in the Ouachita Mountain region, and we have some of the most beautiful quartz minerals coming from that region. And we have the purest, what we call novaculite, microcrystalline quartz, coming from the Ouachita Mountain region. And so this here is a sample of some novaculite that we're right alongside. So this resource is a, of course, non-renewable resource, but something that Arkansas does have. And the quartz, maybe you know this, maybe you don't, but the quartz mineral is Arkansas state mineral. Okay, Arkansas state mineral, the quartz, the beautiful quartz. So these are some non-metallic, so metallic and non-metallic resources that Arkansas has. But those are examples of the non-renewable, but metallic and non-metallic kind of grouped together. Okay. As we continue to look, and again, that little PowerPoint, we're going to be staying on this PowerPoint for quite a little while, but it's going to talk about the hydrocarbon fuels, okay? So here we are, non-renewable again, but hydrocarbon fuels, things that we'll probably go in this order. We'll talk about the gases, then the oil, and then the coal. So almost in the reverse as it's listed in the PowerPoint. So the hydrocarbons. Well, just like the name sounds, it involves hydrogen and carbon in the makeup of it. And the simplest hydrocarbon is known as methane. So I'll write it two different ways here. Here is the sort of chemical formula of what we call methane or natural gas. Okay, so this is methane. Okay, so it's an odorless, colorless gas known as methane. They add a little odor to it so that you could detect a leak, but it doesn't naturally smell like that, but natural gas. So here is the sort of the chemical bonding would look like, with that carbon in the middle and carbon making 4 bonds to a hydrogen atom. So that's sort of the structure that the methane makes. And so methane, when you burn it in the presence of oxygen, it will release energy. Okay, so it's one of our fuels, energy, and it's going to release as a product of water and carbon dioxide. So when we burn our hydrocarbons, we do release carbon dioxide and water. so the releasing of the energy is what we're extracting from it. All right, so trying to get at our hydrocarbon fuels. We're trying to extract the natural gas. And so the sort of the method that they used, I've got some samples here that I'll pop under the camera, but I have some sandstone here, a little piece of sandstone, and I have some shale here. The darker, the black one is shale. I'll write these words up on the board too. But as we take a look at these two, so this one up here is the sandstone, very gritty, rather porous. So a lot of pore space between the little sand-sized sediment particles. So they're able to really soak up all these gases and the oils in the ground, okay, our hydrocarbon fuels. So that one's the sandstone, quite beautiful. And then here we have what we call the shale, okay, so that's the spelling of shale, S-H-A-L-E. Some people think I'm saying a seashell when I say that, but shale. So very fine grained. So there is pore space there, but it is extremely small to the point that we call the shale an impermeable rock. Things don't want to flow through it. So impermeable is that term with the shale. But gases and oils can get in those little tiny pore spaces, but they're kind of trapped in there. Versus in the sandstone, very porous, very permeable. So things can flow through our sandstone rather well. So you can get the flow of the gases and the oils through the sandstone. But the shale, it's a little harder for that to go through. Okay, so we've got this type of bedrock, and sort of the old drilling method that they used to use to extract the oil or the gas. We're talking about the gases right now. To try to extract that, I'll do a little drawing here. So this is kind of the older method here on how they used to get to it. But here we have several layers of bedrock. So shale might be that layer. This one, sandstone, layer. And we'll do another shale layer. So this is something we do see kind of in the Arkansas River Valley area, even in the Ozark region, in the bedrock. You do see interlaying layers, we call them beds, of the stratigraphic rock. Shale, and then some sandstone, and then another layer of shale. So you have sort of this permeable layer, the sandstone, sandwiched in between two layers of shale, the impermeable layers, so things don't really want to flow through the shale. So we're trying to get to the sandstone. The sandstone ends up being kind of under pressure because of those two impermeable layers above and below. And so they will take a drill. I've got a drill bit here. It's actually not as big as they are, but very heavy. And what you can see here, and they can change out the bits on these, the heads here, to whatever type of material they need, depending on what type of bedrock they're going through. So we do have a nice, it's very heavy, drill bit, and they will drill down through the various rock layers and have a pipe extending through. So they have their drill rig here. This will be our little drill rig, let's say, the drill rig. Right, and they get their pipe, and they're going through, drilling down, and they end up in that sandstone layer because that's going to flow through quite readily. And so then that methane gas under pressure is going to want to go right on up. So the methane. That gas, that layer is being under pressure, and it will flow through there, and it will go right on up the drill rig. And so that's sort of the older kind of drilling method. Well, the Arkansas River Valley is where we used to get a lot of our natural gas, but we were starting to kind of run out of that. Remember, this is a non-renewable resource. So we're thinking, oh, it's not going to last much longer, but they came up with some new technology known as hydraulic fracturing, where they could then make use of these shale layers, okay? And so now they could get to those shale layers, break them up, so do a little explosion in there, fracture the bedrock in the shale layer, and then allow the extraction of the natural gas in that method as well. So we actually found a kind of a newly discovered resource of our hydrocarbons. And this was found in the Ozark kind of mountain region, the Fayetteville region. Some of you might be familiar with the Fayetteville region. So right here on our map, the Fayetteville region, point here too, I suppose, right there, Fayetteville. It's known as the Fayetteville Shale. So I'm saying shale, that layer. And so they were able to get sort of a newly discovered resource of the methane gas, or the natural gas. So maybe you've heard of the Fayetteville kind of shale. There's a little bumper sticker on a truck here that the truck was powered by natural gas, and so they say the Fayetteville shale, produced by the Fayetteville shale is what they're talking about in this region. So what they're doing different here on how to get to that shale layer was using the hydraulic fracturing method, so sort of a new method. Call that fracking. Maybe you've heard of fracking, maybe you haven't, but it's a relatively new drilling method where, if I can continue kind of my picture there, again we have the shale layer, the sandstone, another shale. This time what they do, drill rig, they're able to maneuver and allow to go in a horizontal fashion so they can get into whatever layer they want. Let's say they want to go down here to this shale layer, real deep down here, and they start going and tunneling sideways, okay? And they set off these little explosions along the way, fracturing, right? So fracturing the bedrock, allowing a greater pore space, and then the gases can get in there and then by pressure go right on up, okay, the methane would go right on up their pipe, okay, and extracting the methane in that manner. They use, so the hydraulic part of it, they're using water, but also mixed with what we call a drilling mud. It's sort of has a heavy weight to it. It's called barite. Barite here. Pictures of barite. This is a barium sulfate mineral, and it's heavy. It's actually very heavy for its size. It has a high specific gravity to it. It's got quite a heft to it. And so it's a heavy kind of drilling mud that they use to allow the sandstone and the shell, which is much lighter specific gravity, to float up on that drill mud and keep that line opening, kind of sieve out the sandstone and the shale as they are drilling down. So hydraulic, they're using water and this drill mud of the barite, okay, that drill mud in there that kind of keeps that hole open and sieved out of the sandstone and the shale in there. And so this is a rather new drilling method that they were able to discover. So even though we thought, oh, we're running out of our source of natural gas here in Arkansas, with this new drill method, they're able to tap into so much more now because we can get to the shale layer and make use of the shale layer, when before it was only the sandstone layer that we could get the gas from. So I have a little handout here that talks about all the shale resources that kind of across the country actually. But here in Arkansas, this one here is known as the Fayetteville Shale, okay? And so that's sort of our resource, a newer resource here in Arkansas that we discovered that we can tap into the shale layer and get to the natural gas using the hydraulic fracturing. But the hydraulic fracturing doesn't come without a cost as far as environmental problems that can come up. Don't know if you've heard in the news lately or the last several years that we've had earthquakes here in Arkansas, that they get them in Oklahoma a lot. And if you look at these locations, you see that there is that Fayetteville Shale. Oh, right there in Kansas has some shale as well. And so they're starting to get these earthquakes. Well, what's happening is that, all this liquid, all this hydraulic water that they have to pump down in there, they've got to get rid of that. And so they inject it into the ground. And when you inject all that water into the ground, you're basically destabilizing the ground. And so that will cause some shifting to happen, and you will get those subsequent then earthquakes. And so, some people think, this is the new normal, we just have to live with it. But if it's in your backyard, so to speak, it's a little harder to take. And so there are some environmental things, and earthquakes is one of them. Although there are some others that are on this little handout here. Don't know how well that's going to show up for you, but how it works. And so this is a much better drawing than the one I did on the board there. But you can see they can go to whatever layer they want. Notice how they are going through some layers of groundwater, known as an aquifer. So groundwater aquifer contamination, should you get a leak in your pipe, can happen. That's a problem. But they can go to whatever layer they're after. They happen to be after this right here. And you can see the little explosions that they do, the little fracturing. They're running the water through to keep that open. And then they can extract the gas out of there. So yeah, the earthquakes is one thing. Here it is on this list. That becomes an environmental problem from this. Drinking water, so again, they are injecting the waste into the ground, and that can make its way to those very precious aquifer layers, those water layers. So groundwater contamination is a problem. Air emissions as well. So again, some of the pipes do leak, and they are very hard to turn off, these pipes, once you get a leak going. So methane can be spewing out, and they can't get it turned off very rapidly at all. That can really irritate some people's lungs, and so you pretty much just have to evacuate the area should that happen. So air emission problems, water contamination problems, and then the earthquake problem as well. So it was a wonderful discovery, this new drilling method, but there's always a price, there's always a cost, pros and cons of all of these, so in our quest to extract earth resources. Okay, so that's a little bit about the new drilling method. So we always think we're running out of stuff, but then we are very intelligent and we can come up with some new ways to get at it. Some of the good rocks there. So that was the simplest hydrocarbon, methane, the one carbon. Well, these carbons can actually link up and form very long chains. You could get like a 2 carbon, so we can have 1 carbon here, another carbon here, and of course all those hydrogens bonding to it because it's a hydrocarbon. You could get a 2 carbon chain, that would be known as an ethane. 3 carbon chain, that's a propane. And you might think, oh, I'm familiar with propane gas. That's like a grill gas. You've got your grill out there, and sometimes you use a gas, propane. Butane would be a 4 carbon chain. We use a lot of butane in rural areas for fuel. So butane, and you can keep going. So you can do 5, a pentane, 6, a hexane, 7, a heptane, 8, an octane. So you think of the octane fuel, those high energy fuels. So you can really get these to link up. And eventually you link up enough and you can get what we call the oils. So you start to get into the oil category, very long kind of carbon chains. Then the liquid fuels you think of as the oils, okay? And so crude oils and things like that. So how we're getting the oil in the ground in the first place. Do you have any ideas of why do we even have oil in the ground? Where is it coming from? Why is it in the ground? Okay, so we're thinking about non-renewable resources here, and it definitely is a non-renewable. And if I can find my little picture, oh, I've got so many things here, might not be able to find it. Oh, here it is. Little picture I'll put up under the camera for us. Get my little rocks out of the way. Might help you remember where oil comes from. Okay, I want to slowly reveal here. Why do we have the oil in the ground? What is it coming from? Looking familiar to anybody? Keep it going. Now, does that look familiar? That is Sheldon J. Plankton. So oil comes from plankton. And this little image might just help you remember where oil comes from. So plankton, these little, sometimes single-celled organisms that lived in the ocean, floating around, doing their thing. Here we have at the bottom here some pictures of phytoplankton, kind of photosynthetic, little single-celled organisms, and they have very ornate spicules and spines on them to help them maneuver in the ocean environment, kind of protect them as well, and zooplankton. So we have a variety of little organisms that live in the ocean. So we talk about these microfossils. Maybe you heard the term fossil fuels. A lot of people think, oh, we're talking about dinosaurs. That's where we're getting it. Well, not those fossils. So they are these little microfossils of plankton that lived in the ocean. So again, Arkansas, United States, parts covered in the ocean at one point. We're talking millions of years ago, hundreds of millions of years ago, where these organisms lived. And they died, and their little shells would rain down to the ocean floor, bottom of the ocean, and then start getting sediments to cover them. Very fine-grained sediments like shale. And so that's getting kind of absorbed in the shale layer. And then we maybe get a sandstone layer, and it's getting into the pore space. So all that heat and pressure that happens from the layering of the sediment on top of it sort of cooks the little plankton, and the oozes out into the bedrock. Okay, and then we go after the bedrock to extract these. So oil is coming from the plankton. So hopefully that little picture is going to help you remember where oil comes from. Plankton. Little plankton out in the ocean. So the United States is a big consumer of oil, as you can imagine. Huge, in fact. But we have a lot of countries that export oil to us. Yes, we make some of our own here and use some of our own, but we really do like to hone in and import some oil as well. And so if I asked you, what were the top countries that the United States imports oil from? And a lot of people off the bat think, oh, out there in the Middle East, Saudi Arabia. Yes, true. Maybe our neighbors, Mexico, Canada, and some others as well. So I've got a list here that I'll put up under here. Might not be able to see all the details of it, but our neighbors to the north, Canada, is where we get the majority of our oil being imported into the United States. So about 25% there. So Canada is a very big contributor to our foreign oil. Canada is. But yes, there are some others. Here's Saudi Arabia at 15%, Mexico at 13%, and various others. We've got Nigeria, Iraq, Venezuela, Algeria, what else here? Angola, Russia, Ecuador, and they've got varying percentages there, but a whopping 25% come from our neighbors to the north in Canada. And so there is a pipeline in the works. They've already got a pipeline in place, the Keystone Pipeline. There's just an extension that there's just been an ongoing debate. Okay, so here is the Keystone Pipeline map, helping us to bring that oil from Canada to the United States, trying to get down here to Cushing, Oklahoma, where there's a big oil hub distribution center there as well. So all these pipelines to bring it down here. So there's one called the Keystone XL pipeline, which is a new segment of an already existing pipeline. So the red segment here, okay, is where they're going to try to build a new pipeline on this map here. And so this has been in debate for well over 10 years, back and forth. It's on, it's off, it's on, it's off. It's been debated for so long. So at one point, a few years back when Obama's administration, he scrapped it. Said, no, we're not going to do it, blocked it. Trump administration, oh, it's back on the table. We're going to go forward with it. But a lot of judges are blocking it because you're sending a pipeline through a very delicate region. I mentioned aquifers earlier. There is a groundwater aquifer that the pipe is going to go through. It also goes through tribal sacred lands, another issue. So there's a lot of uproar about this. But here is a picture of the Ogallala aquifer. Ogallala is an Indian name that they have for this groundwater resource, an aquifer. And so part of that path of that pipeline is going to take it through, and it's up there, South Dakota, Nebraska, is taking it through that. This is a very precious water resource. This is a big agriculture region. It's, Kansas, the wheat belt, Nebraska, the corn belt. So it's a lot of agriculture, but the important thing about it is they don't actually get a lot of rainfall in this region, in the Great Plains region. They rely heavily on their groundwater to cultivate their fields. So they're pulling with this groundwater resource. So if it gets contaminated, they have a very, very serious issue. So that's a lot of the debate. The latest that I read on it, in April of 2020, a judge had blocked it. So they're all getting ready, getting everything together, hiring people to to go forward with it, but they blocked it because the Army Corps of Engineers didn't quite have their endangered species permit approved, and so they're like, no, you got to hold off on this, and so it got blocked by a judge. So it's on hold for a little bit, and then in May 2020, the Trump administration and the Army Corps of Engineers did an appeal on this. And that's kind of the last bit of news that I've heard about the Keystone XL pipeline. But should this go forward, if it ever does go forward, it would transport oil from Canada to the United States. And so that's sort of the thing about the Keystone XL pipeline. Lots and lots of debate because of environmental concerns and, of course, the tribal sacred lands concern as well. Keystone XL pipeline that's what that's called. It's called Export Limited, so X for export and then L for limited. Yeah, so this is just an ongoing saga, but it really does show you about the environmental impacts that we do have to consider with our extraction of the oils and the gases. So, United States, we love our oil and our gases. Basically, oil runs our economy. And so in comparison to other countries, I've got something here, the top world oil consumers, okay? Could be more now. Again, that's probably not showing up real well in your view there. But 21%, that's the United States. This wedge right here, little old US of A, 20%, 1/5 of the world's oil consumers is us, United States. You've got some others, China, India, Japan, Russia, Saudi Arabia, and so on, and then like everybody else, kind of rest of the world sort of thing. But United States, 20%. I'm gonna round that to about 20%, so that'll be something you can remember easily for the exam. But about 1/5 of the world's oil, United States consumes. So we are really loving our oil for sure. Okay, yeah, about 20% of the world's oil each year. Okay, yeah, so back to this same little PowerPoint. We've talked about the gases, the hydrocarbon, methane, natural gases, and propane, butane, that kind of thing. The oil coming from the plankton, from the living out in the ocean, and then coal. So coal does form within the Earth's surface, and depending on how deep down you go, as you go further down towards the center of the Earth, you have things under more and more pressure, more heat under them, and so it'll compact material much more as you go deeper. And so the formation of coal, I've got some stages of that in your book as well, but this a little image that I have. Coal formation stages, and so the first one we just call that peat. So coal is forming from planty type material over time that of course gets buried. So peat is partially altered plant material. This is very smoky when you burn it, so low amount of energy return from that. It's not compacted very highly. But notice that this is in a swampy type of environment. So the environment, if you have coal beds, you can learn something about your geologic past, because there had to have been a swampy type of environment where these trees were growing, and you would get very rapid burial of your trees, okay? So swampy type of environment. and some way they're getting buried and undergoing some compaction, layer after layer, as time goes by. So again, we are talking millions of years in the making. Definitely a non-renewable resource. We're going to set them out. The first one here, with moderate compaction, we call that lignite. Okay, this first one here, kind of a soft brown coal, moderate energy amount. So we're talking maybe only about a 40% carbon content, so not real high on your energy end there, but still very useful. Arkansas, actually, where'd my map go? Does have some lignite resources in the Warren and Hampton area. Okay, so Warren's not too far from Monticello. So here's Monticello where we are, and there's Warren. So Warren, kind of Hampton region in there, does have a decent supply of the lignite, but studies showed that for it to be cost effective, you really couldn't transport it very far. So the transporting of it ended up making it not very cost effective for the amount of energy that you could get from it. So we don't actually use our lignite, but it's sort of a softer, brownish kind of coal, 40% carbon content. Okay. So we don't really use ours. So Mississippi does use their lignite. But as you undergo more heat, more compression here, so we're getting quite a bit more greater burial, so this would be a little deeper down. We have what we call the bituminous coal. I have a sample of that here. Of the bituminous coal. This is soft, kind of black coal. And there's the coal word there for us. Okay. This bituminous has a little more carbon content. I want to say about 80 to 85% carbon. So a little more energy coming from the bituminous coal. We do use our coal-fired electrical plants do use the bituminous coal here for energy purposes here in Arkansas. We actually import all of our bituminous coal from Wyoming. Okay, so we don't actually produce our own coal here, but Wyoming is where we get our coal here that we use in our coal-fired plants in Arkansas. So the burning of coal there. Then there's another one that actually goes through a metamorphic process. We're learning about the rock cycle and metamorphism, but under more heat, more pressure, okay, we have what we call the anthracite. Okay, the anthracite coal, I do have that, here it is, a metamorphic rock. This is the anthracite coal. And the anthracite coal, I don't know how well that shows up for you, but it actually does have sort of a goldish kind of a sheen to it. So in the light, it kind of has a goldish kind of sheen to it. But the anthracite has undergone metamorphism, and it is very compact, and it has 90 to 95% carbon content. So that's a much greater energy return when you burn the anthracite coal. So different kind of grades of coal formation, stages of coal formation, depending on how deep you go with the burial and the compaction, you can get varying energy trade-off there. So that is the anthracite coal there. But here in Arkansas, we do use the bituminous coal imported from Wyoming here in Arkansas. The burning of coal. So again, there's always a trade-off with all of our quest of these energy resources. We have sort of a nuisance mineral that is in the coal that we burn, and it's called pyrite. So when they dig and mine for the coal, They're also bringing up this mineral called pyrite. So pyrite, I'll stick that under there real quick. Something white behind it maybe might be helpful. See that? I'm not sure. That helps. But the pyrite is an iron sulfide mineralogy to it. So as you're burning the coal, you've got the pyrite mixed in there, and you burn that and you're actually releasing sulfur. So iron sulfide contains sulfur in it. So this is sort of a nuisance mineral in it. It's also known as fool's gold because it kind of has this goldish, kind of looks like a nugget of gold, but it is not gold, but they call it fool's gold. But it has that sulfur content in it, and you can see how it is an iron sulfide, and it releases that sulfur. Well, sulfur in the atmosphere will react with water, and it will form sulfuric acid, and you get what we call acid rain, which is very detrimental. So the acid rain is an environmental problem that we had from the burning of coal. Well, they've sort of mandated, and the Environmental Protection Agency required that all these coal-firing electricity generating plants are to put these scrubbers on their stacks. So as the emissions are going out, they're misting like water. They call them scrubbers, but they're misting water that will go ahead and react with the sulfur that's trying to escape and dampen it down and have that react so that it doesn't actually get into the atmosphere. So they call those scrubbers that they've had to be fitted with to try to help that acid rain environmental problem from the burning of not really the coal, but it's the pyrite in the coal that becomes a problem. So again, there's always a trade-off with our resources and the balance of the environmental problems that come about. Okay, so this is sort of our coal information. Okay, so I do think that took us through the gases, the hydrocarbon gases, then the oil, and the coal. These hydrocarbon fuels, we call them, and they are non-renewable, as you can see, because the processes that produce those take millions, if not hundreds of millions of years in the formation of these. So, okay. Well, and I've already mentioned a couple environmental problems that we do encounter with our quest in extracting and using these earth resources. So some environmental problems and what we consider human-induced, meaning what we are doing, that is a problem with these. So human-induced. We really are trying to find the most environmentally, alternative methods that we can, and cost-effective and environmental friendly as we can. But problems do arise from their usage. There was a gentleman, he's since passed away last year, but a gentleman that I always talk about because it pertains to here in Arkansas. He had a proposal to, instead of really, breaking up all the shale and because of this real nice resource that we had here, this newly discovered hydraulic fracturing kind of thing, instead of oil, to tap into that methane, okay? So he really was trying to push for us reconfiguring our trucking industry, modifying their engines to run on methane. You remember that bumper sticker I showed you about powered by Fayetteville Shale? So he was a big, actually, oil tycoon. He was a billionaire, oil tycoon. But T. Boone Pickens was his name. He since passed away at age 91. But his idea was to set up, again, he's a billionaire, he was going to set up all these methane gas stations along the big trucking highways so that they could power up, fuel up. But T. Boone Pickens, sorry, was his name, an oil tycoon. Okay. And so, yeah, he was an oil tycoon, but he thought of this, this could be good for Arkansas because we had the Fayetteville Shale, that newly discovered methane gas, natural gas resource, and he was ready to invest and build all of those gas stations, the natural gas stations along the way, but he needed to get the trucking industry in on it. So that was sort of the importance of T. Boone Pickens here to Arkansas. But yes, he died a year ago, September 2019. But I always talk about T. Boone Pickens. Yeah, so trying to find these little alternatives to coal, let's say, or to oil. We're always trying to figure out some different methods there. So that was T. Boone Pickens, but some of these human-induced environmental problems. We talked about the acid rain problem, where the burning of the coal, but it's really the pyrite in the coal, that's the problem. So that would have been like an air issue, creating sort of an acid rain out there in the atmosphere. And then of course that rains down and that can contaminate your soil, right? Contaminate your water, making it very acidic, so killing wildlife and such. So yeah, the acid rain problem is definitely one. Air pollution, so those emissions going up in there. It's not just sulfur. Sometimes we get some nitrogen oxide in there as well. But all types of particulate coming off of the burning of the coal. We do get of course, carbon dioxide is a byproduct of burning these hydrocarbons. And so carbon dioxide is another environmental concern with global warming. So global warming is where it actually is happening. People are like, is that really happening? Are we really getting global warming? Well, we do want to look at the data, and I'll have some data here in a little while, but meteorologists are hungry for data hungry people, and they take all types of measurements. And temperature, of course, is one of those. But there does seem to be a correlation between the increasing amount of carbon dioxide in the atmosphere from the burning of our fuels, our hydrocarbon fuels, and an increase in the temperature. They're like going hand in hand. So yes, there is global warming. They do consider that as a human-induced problem, global warming. Another one is ozone depletion. So the ozone layer, kind of two scenario kind of thing with ozone. I don't know if I can find my picture of the ozone. Good ozone, bad ozone. Yeah, nope, not finding it. But it's way up in the atmosphere, high up in what we call the stratosphere, a layer within the atmosphere, above where all the weather takes place. That's the troposphere. But way up there in the stratosphere, 30,000 kilometers up, we have our layer of ozone. So ozone is a triatomic molecule called ozone. Its little chemical formula is O subscript 3. Oxygen, by the way, is O subscript 2. But this is a triatomic. Triatomic molecule of oxygen, and it does us a great service having it way up there. This is the good ozone because it blocks the majority of the UV radiation, the ultraviolet radiation coming from the sun. And so you've maybe heard of UVA and UVB. Well, there's also a UVC, and those are lethal, damaging rays. A little bit of UVA, a little bit of UVB does make its way through, and that's why you do want to wear your sunscreen if you're out, because if we didn't have that ozone layer, we would be seeing skin cancers on the rise, cataracts with our eyes on the rise. So we need that ozone layer way up high. That's the good ozone. Ozone does occur closer to the Earth's surface, the ground surface, and that is not so good because people with lung disorders, asthma, COPD, different things like that, it will adversely affect them. You have your ozone days where you either need to stay home or carpool or something like that. But the good ozone, way up high, protects us from those damaging UV radiation. So there was back in the 70s talk of this ozone depletion where we were getting a hole in the ozone. It really wasn't a hole, but it was a thinning of the ozone layer caused from what we call these CFCs. Okay, so CFCs, fluorocarbons. We think about how I was drawing that methane earlier, right? It was a carbon with 4 bonds around it, and methane was hydrogens all around it. Well, this one we have the chlorine and fluorine molecules. So they call them chlorofluorocarbons, chlorine and fluorine in this molecule. Okay. What it is, it's really the chlorine that's the problem, because the chlorine is going to react with and break apart our ozone molecule. It's going to break it into an oxygen molecule and a single molecule, or just a single separate oxygen atom. It breaks it apart and binds with it. And so it doesn't allow it to reform in the O3, the triatomic structure, which is ozone. And so as we were burning and emitting these chlorofluorocarbons, which were put in as a refrigerant, like a freon type of material, our refrigeration of our electric coal-firing plants. We needed to keep those cool and the energy and electricity for that. Yeah, we were putting freon in that. So refrigeration systems were putting these into the atmosphere. And that chlorine is actually still there, but the Environmental Protection Agency did ban the chlorofluorocarbons, and so we're no longer using that chemical formulation for our cooling agents. So we've changed that up a bit. So we're not releasing any more of that, but we've still done damage up there that, hasn't been repaired. So that is definitely, the ozone depletion is a human-induced environmental problem, in addition to the other ones that we had talked about there. Some other things to think about environmental problems, which is these are natural hazards. Not a lot you can do about these, but the earthquakes, right? So we'll be learning about earthquakes, where we see them in the world. There's a definite pattern to our earthquakes, natural earthquakes, not the man-made ones that we were talking about through that hydraulic fracturing process. That's human-induced. But we're talking about Earth's normal or natural functioning. We do get earthquakes. The plate tectonics, the plates are moving, and so you are going to get slippage of the Earth. Volcanoes. So our volcanism, natural hazard as well, and we'll be looking at, well, where do we see our volcanism on the planet. So other than just not living next to a volcano, there's not a whole lot you can do. That's a natural hazard. Other things like floods and droughts, these are natural kind of cycles. You can get in a blocking pattern in your weather system, and it can train rain over the same area for days and days and days and days, weeks, and you can get the flooding, the droughts, same thing. You're in a blocking pattern with a high pressure, sun beaten down, and so you can get into some droughts. And these are what we would call natural hazards. And of course, the earth scientists, the meteorologists, environmentalists are all trying to look at and try to solve some of these things. But you know, it's the earth. It's going to do its thing. Human-induced problems, we can have a say about some of these things. So those are some of the environmental problems. And again, the earth scientist is trying to find a balance. They help to solve problems with our quest in extracting and using earth resources the most economical and environmental friendly way is sort of their goal here. Those are some of the environmental problems that we do see. Lastly here, the scientific inquiry. So this is sort of every science class is going to give you an overview of the scientific method, ways of kind of knowing, giving you some significant insights into understanding how the natural world works. Okay, so one thing is that we do assume that the natural world is consistent. So we have consistent laws that we go by, scientific laws, that we can kind of predict things because of it. And I keep going back to the meteorologists because they have lots of data that they look at, and part of what they try to do is to predict the weather in our weather forecast. So we have some consistent patterns that tend to come together, and they'll look at those patterns and see them, and they're like, okay, I kind of know what's going to be coming. So they're trying to predict for us, and that is what science does. So we do try to, I think I went forward a little fast there, do try to predict with science, the goal of science. So goals, trying to discover patterns in nature. So we just kind of do that as humans, looking for patterns, trying to group things. This is similar, this isn't, and we just do that in our ordinary daily lives without even realizing it, I think. But we want to be able to use that information and predict future events. So that's sort of the goals of science. But we talk about various types of knowledge. These aren't on your PowerPoint, but I'm going to include some of it. One of them is called empirical knowledge. So empirical knowledge talks about knowledge we can gain from gathering data. So measurements, observations, and these are what we call the empirical. So I'm going to write that word up, empirical knowledge. Okay, so some ways of knowing here. But empirical is we are looking at the data, observations, okay, not reading anything into it. We're just collecting and accumulating our data, so accumulation of data. And we're doing that through measurements, through instrumentation. We are gathering the data. Okay, collect the data. Another one is called theoretical. Theoretical knowledge. And this one is how we try to come up with an explanation of the data that we have accumulated and collected. So they kind of go hand in hand. The empirical, here's my observation, here's my measurement, I've collected that. Now we take it and theoretically try to explain the data. Okay, so trying to explain the data. It's an explanation of the data. Of course, these first two are what we consider scientific knowledge. There is a third type, and I'll go back to these two here in a second. There is a third type that we call dogmatic knowledge. The third one here. Dogmatic knowledge or dogma is where an authority figure of some sort, whoever makes them the authoritarian, okay, has a certain set of beliefs and they say this is how it is and it's incontrovertible. It's just true because I said so, kind of thing. So that would be dogmatic, sort of a set of belief system. Politics use that a lot, but this is non-scientific. Okay, non-scientific. First two are scientific, non-scientific. Okay, so a belief system, so religion would fall under that category. Politics is another one. Okay, so a statement, something in religion, say, in the beginning God created the heaven and the earth. Okay, that would be dogmatic knowledge. Okay, non-scientific though. Okay. These other two are in the realm of science. So accumulation of data, and if you remember, I keep talking about the meteorologists because they really do collect a lot of data. Here it is. Let me go to that real quick. So this here is the amount, I can't get it all in one screen there, but it's showing the amount of carbon dioxide parts per million in the atmosphere way back. So we're going 800,000 years ago. You're thinking, we didn't have any meteorologists 800,000 years ago. How do they know this? What they do is they drill down into those huge glaciers. So the further down you go in a glacier, or in a rock bed, farther down you go, further back in time you're going. And so they'll drill down and take out a core of the glacier, and they will study it. They will take a little warmed up needle and go in and extract out a little pocket of air that got trapped as that ice was accumulating. Okay, it's accumulating, there's a little bit of air back in that little pocket. And they will extract that with a syringe, and then they will test it for the amount of carbon dioxide in it. And so they could measure parts per million the carbon dioxide, and they've done this, and they say, okay, yeah, so we were sort of in a warmer interglacial period, not as many glaciers going on, carbon dioxide, one down here we are in a glacial or an ice age, and so the amount of carbon dioxide will kind of just naturally fluctuate. This is before humans came on the scene even. The burning of those fossil fuels, right? But at any time, really, in Earth's 800,000 years, as far as they went back here, the parts per million of carbon dioxide never went above 300. So right there, that was the highest previous concentration that we found with this information. Then we take a look, and this is a little old yet, it was 2016, 2020, we've actually gone well above, maybe 410 now. But at this point, you notice something different is happening, and And this happens to coincide with the Industrial Revolution, when we began burning the fossil fuels, right? These hydrocarbon fuels, and releasing carbon dioxide into the atmosphere, and it went up, up, up. As you can see, went way above the 300 parts per million. In 2016, it reached 402.9. It's actually been recorded as 410, 411 parts per million. You know, and they come out with these every so often. In 2019 time frame there, something is happening. So the amount of carbon dioxide is increasing due to the correlation is there, due to that burning of the fossil fuels. So things that we are doing as humans, putting that carbon dioxide in the atmosphere. So that's just one part of the equation. We look at that data. We're looking at the empirical data, parts per million of the carbon dioxide in the atmosphere. Well, something else that they've been looking at is the temperatures. So carbon dioxide is what we call a greenhouse gas. And what that means is carbon dioxide will trap terrestrial radiation. So sunlight comes in, shortwave radiation, things on the planet absorb it and re-radiate it in a little bit longer wavelength known as terrestrial radiation. And the carbon dioxide in the atmosphere will absorb that terrestrial radiation and re-emit it back downward towards the planet's surface by warming it. So we're trapping the heat in. And we are thankful that we do have sort of that greenhouse effect, because it keeps our planet comfortable within some normal temperature ranges. So, but if you get way too much, your temperatures are going to increase and increase. And that is what we are seeing by taking a look at the temperature readings. And so here we've got annual global temperature, and what they're doing is their zero line here, if I can get that scooted over, this zero line here is, again, climate kind of tends to go with a 30-year average of things. So from 1951 to 1980, they took the average global temperatures, this is globally, and made that, whatever that global average was from that 30-year time period, they made that their zero line, okay? They made that the zero line here. And then they took a look at and saw, okay, as we went through time, were we above or below that average, okay, that zero line there. And so as you can see, yes, we are trending. Here we are in 1970, 80, 90, 2000, 2010, and here we are 2020. And it's actually, you see that went down there. It actually, our highest that we had, our highest recorded temperatures in 2018. So it did trend upward, continuing to trend upward. So hand in hand, as the carbon dioxide is increasing, parts per million in the atmosphere, the temperature are increasing. This is globally, okay, not just in Arkansas. So yes, we do see the empirical knowledge, and then they do an explanation of the data, and the correlation is very strong that what we are doing as humans, the fossil fuel burning, the hydrocarbon fuel burning, producing all that carbon dioxide, okay, a greenhouse gas, is we are seeing that in the data as temperatures are increasing. So global warming, an explanation of that data is this human-induced from the burning of fossil fuels. So that's a little bit with the scientific knowledge that we can gather, so trying to explain the data. So yeah, those are scientific. Okay, the last couple of PowerPoints in here. So our natural world is consistent and predictable, right? So we do try to predict future events. Gathering facts through observation, so trying to collect our data. Then we try to formulate hypotheses. So this is just a single kind of conjecture or idea that we have, and we're putting it out there. That's a hypothesis, basically untested. We're just putting it out there. This is what we think. This is our hypothesis. We need to either accept it, modify it, or reject it altogether and start over with a different idea with a hypothesis. Okay, definitely we need to get tested. But a theory, a scientific theory is very elevated in our scientific realm. It does pack quite a stout caliber to it. It's elevated. So it has to be tested. You can't just throw something out there kind of thing. It has to be tested, verified, confirmed, okay? So in science, say you got to go with all the, the physicists, right, meteorologists, geologists, the planetary scientists, so the astronomers. You cannot go against any of the laws of chemistry, biology, and etc. So it has to be tested and confirmed by sort of your peer, other scientific review committees before these would be accepted, right? So confirmed. So they're used to explain the observations and predict future events. So prediction is really a big part of science there. We need to be able to predict future events for this. So then you actually have another one, I don't think it's on here, but a scientific law. So these have been tested repeatedly. The law of gravity, those thermodynamics and different things, laws are even higher than theories. So the most widely kind of accepted things, the scientific theory, majority do accept those. And that's sort of a scientific method, scientific inquiry, but the scientific theory is taken very seriously at a very high standard in science. So it's just not a theory like you have, I have a theory on that, kind of our casual talking. No, you don't have a theory on it, you have an idea about something, right? But a scientific theory is really elevated to a very high standard. It has to be tested multiple times, every which way, conceivable way, and a vast majority do accept it. It's the most explanatory of your data for what we know right now with the instrumentation that we have right now. So it's the best going explanation. This is a scientific theory. I think that might be the end for us. So that does conclude the introductory chapter. And so if you have any questions, make sure that you do get with me. This is a nice thing to pause and review as needed. A nice supplement to your other resources that you have on Blackboard. So I will see you